Hello everyone, this is Alexey, and today I want to show you yet another tutorial on using Libra. And today, actually, the topic will be our the topic of our tutorial will be the using generating the random numbers, but such random numbers that are also correlated in time in a special way. So, and also we'll talk about autocorrelation functions and their Fourier transform. So here's this run is already a working script. As you can pause and you can actually see what it's there. But I want to kind of walk you through it in this example. So basically, what I added here in the header is basically import of the standard libraries of Python, and then we add the locations where the Libra specific libraries can be found, so that the Python can use them. And once we have added them in this way, we can call this from Libra PY, from SIG Libra core, and so on. So the good thing about this part is actually that it will work all the time. Although I mean, in this case, it's you have to be very precise where you are. So this is like, so your present location is relative to the location of these libraries, but you can also use the absolute passes as well. So then if you have this, you don't need to set up Python pass in the bash profile, for instance. Okay, so that is just a minimal setup. So now I want to generate, first of all, let's create a random number generator class, and then I will want to generate a number of uniformly or maybe normally distributed random numbers for I in X range n, and then we'll get it this way. So G is maybe no, R will be our random numbers, 1 2 1 2 R, and then we'll do append, and then here the random numbers will be just R and D, and then normal. So that will just generate a set of random numbers. Then so these numbers will be not correlated. So how do we know that? Well, for that we can use the ACF function. So this is the correlation function, autocorrelation function. So right, so what it does, it takes this data R, and then it centers data. So for that you will use the ACF module of the Libra PY, and then it will generate a normalized autocorrelation row. Well, this is row, and this will be the time axis. So we of course need to do a few things. First of all, this R is supposed to be a list of vectors. So that means here we'll be doing this. We'll be, okay, let's call it xi, and then that will be vector of R and D normal, and then 0 0. So it's a three-dimensional vector, but here we care only about the x component. So this is psi, and we add it here. Then this module can center it, so the average of the data is 0, and then it just will place and then we'll compute the ACF, and here of course we'll need to define dt. So let's call dt is 1. Now let's just see if that works. So here I do Python and then example py. Ooh, of course, by Python. Here by Python. Okay, so invalid syntax. So let's look at that part for or I in X range. Okay, so it's in X range. Now it's working. This whole warning messages are not important, so that's nothing wrong with that. And other than that, we have no other problems. So everything works fine. Now here I have the file ACF.txt. It's not yet generated. This one I will also delete. Now what I'm going to do is this. Wait a second. No. Is this. So here I'm lazy, I'm copying everything, but I'm doing this step by step. So here now we want to, we might want to, fit this data, but let's not do this for now. Actually, we will just print out this information, right? And I don't know if you can hear my cat is meowing, but that's what I can hear. Okay, now here, since I copied, I want to delete something, this last number and also this other number, and then we can also, maybe remove this part. So now T contains all the time axis numbers. These are normalized ACF and these are unnormalized ACF, and everything and we will be printing everything into this file. So now let's run this example. Oops. And of course here we'll need to, since I changed this row, it's not row, it's another row. Right, so then we can, now it's done, and what it generates is this file with all the numbers, and here it's our time axis, here is our normalized, and here is unnormalized autocorrelation function. So also know that we have only 50 numbers in the ACF, and which is just a half of the total number of the points. We have 100, but that's basically just how it's defined, right? Now we want to plot this data, and here we'll just comment this part, remove this slash, and basically we are ready. Let me do this GNU plot, and we can do GNU plot. Now we have this PNG file, and that's what you see. So these are initially uncorrelated numbers, and you can tell this by looking at what happens here. Like this is a autocorrelation function. It drops to 0 and then fluctuates around 0 almost immediately. Now that's the point. Here we want to correlate this time data, and here is actually the resource. You can read how to do this in this nice document, and this is actually already implemented in this example. So here I'm changing my code. So instead of just normally distributed numbers, I will be putting something else. So what I'm going to do is this. I first generate my random number as I did before, but then my next each next number will be the previous number I generated, times some factor plus another factor, and then plus that new random number. So maybe, okay, since let me do this. I'll do this psi, which I already have, so I don't need a g. Now I need to take care of this r's, right? So since I will start from 0, and then here we'll have something negative. I don't want to start with 0, so that's that's what I'm doing here. Here I'm starting from 1, and then 0 element will be this. We will append. No, actually we don't need to append, so let's just make it a vector with one of the normally distributed random numbers. Okay, so that's our R0 essentially. So then we know R0. We now at every iteration will generate random psi, and then we can get the next one. And then here we don't need to append. Well, okay, yeah, we do need to append, so let's do it this way. So append all this stuff. Yeah, I mean you can pre-allocate the memory for that array, but here I will be growing it you know, step by step, and I always have the access to the previous number. So now what is this f? F is actually mass exp minus 1 over tau, where tau will be our correlation time. So here let's do tau 10, and then we can generate this sequence of random numbers. Okay, here's done, and then let's plot this result. Now this is what you get. You start from, well, this is normalized. You start from 1, and then it goes to 0 within, so this will be like 50, and then 10, I think there will be somewhere here. So probably some conversion factor, but eventually you can see that you don't have anything. I mean, the ACF does not decay to 0, at least you know, very rapidly. So it decays. It doesn't actually go far than that. Well, and different realizations of these random numbers, of course, will give you different results. But in all cases, yeah, you will see something like that. You know, some slow decay of this, and there will be some oscillations of the autocorrelation function, but they're not as fast as what you had before when you had uncorrelated data. So let's actually try increasing this set to a little bit bigger number. So 1000 we generated, and then let's plot ACF. So this is what you have. If you have 1000, so this is 500. So this is initial decay. Well, kind of on the 10 steps time scale. Now let's maybe do the last example here before I run out of time. 100, and then I can run this example. And visualize what we have. Now you can see that these numbers have even slower oscillations. So this is basically the end of my tutorial on generating random numbers that are correlated in time with a specific you know, time correlation time. And maybe later I will be talking about the Fourier transform of the ACF function.